Hello everyone, welcome to Brain Blitz Audios. In this episode of Mind Maps, we'll be dealing with the 7th chapter in the physics syllabus of grade 12 CBSE. And this chapter is pretty important in our daily lives as well as our studies. The chapter's name is Alternating Current. And as always, we use the help of a mind map in order to explain this lesson to you in an easy way. Mind maps are pretty simple and effective tools for last-minute preparations for any exam. However, like this one, they can be pretty extensive, and therefore this video is devoted to explaining each segment of this mind map in some detail. As you can see, we have 14 segments, and we'll be explaining each of these one by one. Let's begin. So, what is alternating current? That's the big question. Now, so far in grade 12, we've been studying sources that have been DC, and DC is direct current. So the current that we usually had in our experiments so far usually only had a single direction, so it flowed in one direction only. But that is not the type of current that we get in our electricity supply through the transformers, through the wires, etc. that flow through our homes. That current is not DC. That current is known as AC or alternating current. And so in this chapter, what we're going to do is we're going to take a deep dive into alternating current. We'll find out who contributed to alternating current, and we'll look at some properties of the AC current, and we'll look at some quantities such as impedance and reactance. Then we'll look at 3 types of resistance that we'll be finding here. 1 from a resistor represented by R, 2 from an inductor represented by L, and 3 from a capacitor represented by C. So we'll have a circuit with only inductor, a circuit with only a capacitor, and a circuit with only a resistor. Then we'll move on to dual circuits such as LRs, so that is inductor and resistor. Similarly, inductor and capacitor, and then in capacitor and resistor. And then we'll move on to a complicated circuit known as the LCR circuit. And this is one of the most important circuits because it's most of the current that passes through our daily circuits such as wires, etc. usually follow the LCR circuit formulae. And then we'll be looking at the power that is present in an AC circuit, and this is one of the reasons why AC current is pretty dominant, because the power loss is pretty low. So we'll find out how that happens. Then we'll look at an AC generator, which is a device. And then we'll finally look at a transformer, which is also another important device in modern day circuits. So that's all in all about the chapter alternating current. Let's move on to the details now. First, contribution. In 1883, a Serbian-American scientist named Nikola Tesla constructed the first induction motor at the age of 27 years only. So this is one of the most important steps of alternating current. So Tesla was a strict proponent of alternating current, and he was pretty prominent in his fight with Edison. So there was a war in the US, and that was between Tesla and Edison about which current needs to be used for circuits. And ultimately, Tesla's argument won, and we're still using alternating current today. So that is some of the contribution that we have to study about alternating current. And Tesla was a smart mind, because by this statement, you'll understand that he just created the first induction motor, that's the AC motor, at the age of 27. So he was pretty bright. So that's the contribution. Let's look at in some more detail about the AC current itself. What is AC or alternating current? So the main property of AC current is that the direction of the current changes alternatively. So that's its main difference. So in DC, it usually existed in one single direction. However, in AC, So let's say we have a time period of t, let's say capital T. So the alternating current would flow in this direction for, say, t by 2 seconds, and then in the next t by 2 second, it goes in the opposite direction. So basically, when this happens, the total would go on to be 0 if it was a vector, but it's not. So that's the main advantage, disadvantage, and important property of alternating current. It changes its direction with every half period. So it changes its direction alternatively. The current is described as I naught sine omega t. I is the AC current. But what is I naught? Now this is interesting because since alternating current has this property of frequently changing direction, I naught represents the average current in a particularly long time period. And sine omega t is the sine ratio of the direction which the alternating current takes in its journey. So that is forward, then backward, and etc. So when we're studying alternating current, we also study it with voltage. Voltage and current are inextricably linked, as you've studied in grade 10, using this relation for DC sources, V is equal to IR. So we'll be trying to expound on this in this chapter. So voltage is also pretty important, and it's important to know how we denote it. So V is the voltage of the AC current itself, and V naught is the voltage of the average current. So we have an average current. So then the voltage of the average current is V naught. And then sine omega t would represent the direction. So now we'll look at some values of AC current. Now these values are normally used for converting it from AC to DC. So in DC, when you say I is equal to 1 amps, you know it's the same value. However, in AC, this current has the property of changing its direction. So we need to find out some other values of current, which kind of tweaks it a bit, but then it gives us the right answer of which current is present. The first is the RMS value. Now, RMS is the short form of root mean square. We need to find the root mean square value of current and voltage. So we know the average current, that is I naught, and average voltage, that's V naught, just simply divided by root 2. So you need to find the IRMS, just divide I naught by root 2. And similarly, you just divide V naught by root 2 to get the RMS value of the voltage. Now, we need to find out the mean value. So this is the actual average. The other one is by experimentation, but this is the calculated version of the mean value. And to find the mean value, what we do is we multiply I naught with 2 and divide it by pi to get I mean from I naught. And V mean is obtained in the same way. So V naught is multiplied by 2, then divided by pi. Next, we need to find the peak value or the maximum value. So we know that this current alternates its direction. So at a particular instant of time, say dt, we need to find the maximum value of this current. So the average current that I've been talking about actually refers to peak value. So this is the value at a particular instant. So I naught is root 2 into IRMS, and V naught is root 2 into VRMS. So you can actually get this by using the previous formula. So these two are interconnected. So that's the segment AC current done. Let's move on to the next segment where we look at two values, impedance and reactance. Now in our study of alternating current, we'll be having a lot of resistors. We'll be having actual resistors, we'll be having inductors, and we'll be having capacitors as well. Now all of these generate a sort of resistance. So the term impedance refers to the ratio of EMF applied and the current produced in an AC circuit. So E naught, which is essentially potential difference. EMF is always potential difference, even though the expansion is electromotive force, divided by the I naught. So these are both peak values. Peak voltage, peak current. So the quantity of peak voltage divided by peak current is represented as Z, and Z is known as impedance. And it's also measured in ohms, which is also the unit of resistance, that is R. Let's look at the next quantity, that is reactance. So reactance is the hindrance offered by the inductor or the capacitor, or both, to the flow of alternating current. So this is the resistor that I've been talking about. So usually in an ideal situation, both an inductor and a capacitor have zero resistance. However, due to the workings of the inductor and the capacitor, they offer some hindrance, and that hindrance is known as reactance. So for an inductor of self-inductance L or for a capacitor of capacitance C, they have a reactance X or chi. The symbol here is chi, but we can also use X to represent the same thing. So now let's move on to the inductive circuit. Now in an inductive circuit, we have potential difference. This is a battery, not a capacitor. So we have some potential difference. And now we have our inductor. So this is a coil. So this has self-inductance L. And so because of this inductor L, there is a hindrance, which is known as reactance. So the reactance due to the inductor is known as XL or chi L. So we need to find out the current, the value of the current that is passing through the inductor and through the circuit, which is an inductive circuit. So I is the value of current in the inductive circuit, while I naught is peak value. Now, in most of the questions in this chapter, they give you peak value or the RMS value. So this value is pretty important. You need to study it. And then we have sine of omega t minus pi by 2. So omega t is the direction, but what is minus pi by 2 doing? Now, minus pi by 2, which is represented generally as phi, is the phase difference between V and I. You see, alternating current, it varies sinusoidally with time. So suppose we have this for voltage, then the alternating current diagram would be something like this. And if you studied your trigonometry well, you should know that there is a difference of pi by 2 of the values. So while this is at 0, this is at the value for minus pi by 2. And then when it reaches 0, then it becomes pi by 2. So there is a difference of pi by 2 between them. And so this difference is known as phase difference. And it's represented using a phasor. Phasor is a vector that represents only the direction. So it only finds out the directional difference between quantities. So here it finds out the difference between voltage and current. So this is V, and the dotted one is I. So phi here is pi by 2. Now to find out the power factor of any circuit, so we already know the phi. So now we find the cos ratio of the phi. So over here it's cos of pi by 2. And cos of pi by 2, that is cos 90, is equal to 0. So the power factor here is 0. Now, since there is a difference of pi by 2 between the values of voltage and current at a particular instant in time, and voltage is actually in front and current is in the back. So here it's 0 for current, while voltage is pi by 2. So what we say is voltage leads current by pi by 2. So it's moving ahead by a phase difference of pi by 2. And P, that's power, is equal to 0 because the power factor here is equal to 0. So that's one circuit done, inductive. So we used an inductor in a circuit and found out the current passing through it. What about a capacitor? So let's study about capacitive circuits. So in capacitive circuits, we have a capacitor, and then we have a battery here with some EMF, with some voltage V, EMF E, and then the capacitor has some capacitance, say C. And now we need to find out the current that is passing through it. Okay, so it's from positive, not negative. So we need to find the I that's passing through this capacitive circuit. Now, the equation given here is I is equal to I naught sine omega t plus pi by 2. I refers to the current in the capacitive circuit. I naught is again peak value of current. Omega t is the initial direction. Sine is the sine ratio. So here we have plus pi by 2. So what happens here is that now, let's say this is for current. This is I. So now we have the dotted line for voltage, and there is a difference of pi by 2. So now you see current is moving ahead of voltage. And so current leads the voltage by pi by 2. Because when voltage is 0, the current is at the cost value of pi by 2. And again, since we know the phase is pi by 2 or minus pi by 2, the direction doesn't matter here. The minus sign doesn't matter. The value of cos will always be 0 because cos 90 is equal to 0. So when phi is pi by 2, it is 0. So since the power factor cos phi is 0, so this is the power factor. That is 0. So the power of passing through this circuit is also 0. Now let's look at a resistive circuit. Now this is pretty similar, but now we're having an AC current. So there is a direction involved. So there's direction involved in this scenario. So we have a resistor of, say, R ohms passing through a normal circuit. And so now we need to find out the formula. The formula for the current I in a resistive circuit R is I naught sine omega t. I naught is again peak value, and sine omega t is the direction change. Direction because it's alternating in every half second. But if you notice the diagram, sine diagram for this circuit, both are following the same path. There is no difference. So when V is equal to 0, I is also equal to 0. So that's the graph for this circuit, a resistive circuit. So what it says is that there is no phase difference. So phi is equal to 0 and cos 0 is equal to 1. So our power factor is equal to 1. So there is maximum loss of power. So the power here is equal to VI. VI is the formula that we studied in power in the chapter current electricity. So electric power is equal to VI. So we're using the same thing here, except that we'll be using V naught and I naught to represent the peak values, and then divide the whole thing by 2. And since there is no difference in the phase diagram, we say that current and voltage both are in the same phase. They follow the same path. So now let's move on to combinations. The first combination is LR circuit. Now in an LR circuit, you have an inductor L along with a resistor R in the circuit. So the current for the LR circuit, that's I, is equal to I naught peak value into sine omega t plus phi. Phi is the phase difference. So there is a phase difference here. It's not like there is no phase difference. There is a real phase difference. And in combination circuit, we use the quantity known as impedance, where we find out the hindrance produced by a set of, say, resistors or inductors, and say resistors or capacitors. So when 2 or 3 of these are coming together, we use the quantity impedance instead of resistance. So we use the impedance Z, and Z, the value of Z is equal to the root of R square plus XL the whole square. Now, R is the resistance, and XL is known as inductive reactance. So if you go back to the previous part of this video, you know that both inductors and capacitors don't have any resistance. However, they have a sort of hindrance to the alternating current that passes through it. And this hindrance is known as reactance. So when an inductor with a self-inductance L is doing this, the quantity that we get of the hindrance is known as XL, and it's called inductive reactance. So when we square the sum, so when we sum up the squares of both these two quantities, and then we do a square root over them, we get the actual value of the impedance. So Z is equal to root of R square plus XL square. And the value of XL, since we have L, the self-inductance as L, and then we have a quantity omega, we get the value of XL, that is inductive reactance, as L omega. Now this is the general formula for inductive reactance, and this is applicable almost everywhere. Now over here, tan phi is the ratio between XL and R. So that is represented as tan phi. So that's the tan ratio of the phase difference, phi. So tan phi is equal to L omega, which is the value of XL, divided by R, which is the resistance. And to find out peak value of current, what we do is we find out we know the peak value of EMF. So that's E naught is the peak value of EMF. And so we divide it by the total impedance, which is R square plus chi L the whole square, the whole root. And so this will be the value for peak current. Peak current. To find the power factor here, which is cos phi, we use this equation, R by Z. So for a circuit containing a resistor and an inductor, we divide the resistor divided by the impedance, the total impedance Z. So in effect, what we're having is a triangle. And so we have an angle that is phi. Phi is the phase difference. So the hypotenuse will be Z. The opposite side would be L omega. And the adjacent side would be R. So this is the graph that we get when we're doing an LR circuit. So let's now go over to the next circuit, which is the LC circuit. So in an LC circuit, we have an inductor and a capacitor. So inductor of self-inductance L and a capacitor of capacitance C are in the circuit. To find I, which is the current passing through the LC circuit, what we do is we multiply the peak value of current, that's I naught, into sine omega t plus minus phi by 2. So omega t is the direction of the current that is in every half period, and then plus minus phi by 2 refers to the quantity phi, that's phase difference. The phase difference is plus minus pi by 2. So over here, the impedance Z is restricted to the quantity X, and the value of X is XL minus XC. Now X is impedance, and X is reactance, and the total reactance is given by the reactance. So this is inductive reactance minus XC, which is capacitive reactance. So we have both reactants and then we subtract them. So we subtract the capacitive reactance from the inductive reactance. And this total value of reactance chi will give you our impedance Z. So Z is the impedance, while chi or X refers to the reactance. Now there is no value for resistance here because the circuit is LC. There is no R. There is no resistor. So there is no resistance. There is only reactance. So the hindrance provided in the circuit is caused due to the reactance of both the inductor and the capacitor. Now, as you have seen, phi, the phase difference, is equal to pi by 2 from the equation. And since phi is pi by 2, cos phi is equal to 0 because cos 90 is equal to 0. So the power factor is equal to 0. So we have two cases here. So either the voltage can lead the current or the current can lead the voltage. And that's the reason why we have plus or minus in the formula, because both cases can occur. So that's LC circuit. Let's look at this third type of combination, which is RC circuit. So in RC circuit, we have resistors and we have a capacitor. So resistance R, capacitance C in the circuit. And we need to find the formula of the current. So the current passing through an RC circuit is given as I naught, which is again peak value of current, into sine ratio of omega t. Omega t is the frequent variation of the direction of the current, because it's alternating, not direct. So there is frequent alternation after every half second. So that is represented by omega t, and minus phi. No, not minus, it's plus phi. So sine omega t plus phi. And phi here again represents phase difference. When we have a resistor, the value of the impedance will be equal to the square root of the sum of the squares of both the resistance and the hindrance produced by the other equipment. So here it's a capacitor, so there is a capacitance C in it. So the hindrance produced is XC. This is capacitive reactance. And so the impedance here, which is the total hindrance, is R square plus XC the whole square, the whole root. So we have the square of this value, the square of this value, we've summed them together, and then we use the square root on top of it. So that's the way we find out the impedance of an RC circuit. And we find the value of XC as 1 by C omega. So that's another general formula for XC. So we find the capacitive reactance using 1 by C omega. And again, to find out tan phi, which is the tan ratio of the phase difference, we use the formula 1 by C omega R, 1 by R C omega. So again, what we get here is Z here, and then the adjacent is R, the angle is phi, and the opposite is 1 by C omega. So this is the triangle with which we're dealing with. So this is the direction. So this is a simple representation of the direction because we're using tan, so we can make it into a right angle triangle. And then to find the peak value, what we do is, again, we use the E naught, that is the peak value of the voltage or EMF, divided by Z. Z, again, is the impedance. The impedance here, that is R square plus XC the whole square. So the value will be E naught divided by R square plus XC the whole square, the whole root. This will be equal to I naught. And the power factor will be R by Z because it's cos phi. So cos of phi is R by Z. And R by the value of Z would be R square divided by R square plus XC the whole square. And so over here, the important thing to note is that the current is always leading. That's why it's given as plus phi only. In the other case, both current or voltage can lead, but over here only current leads, so it's I naught sine omega t plus phi. So we hope you found the three dual circuits interesting. Now we move on to the whopper of a circuit. That is the LCR circuit. So in this circuit, we have all three hindrances present in that circuit. We have an inductor of self-inductance L. We have a capacitor of capacitance C. And on top of that, we have a resistor of resistance R. So to find out the value of the current in the LCR series circuit, once again, we multiply the peak value of the current, that's I naught, with sine omega t plus minus phi. So that gives us, so phi gives us the phase difference, and sine of omega t plus phi would give us the rate at which the alternating current alternates. So again, phi is phase difference. Again, so since we're in an LCR series circuit, what we do is we need to find out the total hindrance. That's the hindrance produced by both L, C, and R, by the inductor, the capacitor, and the resistor combined. So what we get is Z is equal to R square plus XC minus XL the whole square. So XC is 1 by C omega minus XL is L omega. So we have to square this as a whole and then add it with R square and then do a whole root of it. So that is the value of the impedance of an LCR series circuit, the total hindrance of an LCR series circuit. And again, the total hindrance, that is chi, is given by XC minus XL. So that is given by 1 by C omega minus L omega. And tan phi, which is the tan of the phase difference, is again 1 by C omega minus L omega divided by R. So that means this is R and this is the angle phi. And then we have the X, that is 1 by C omega minus L omega. And then we have the impedance, total impedance Z. And so to find the peak current, we again use the same formula. We find the peak voltage and divide it by the impedance. So now we get E naught divided by R square plus 1 by C omega minus L omega. And we whole square that, and then we do a whole root of the total denominator. So that is all about the LCR series circuit. So now we move on to the next big topic, the power in an AC circuit. So power in an AC circuit. So in normal classes, we've learned that power is equal to V into I, and this is for DC current. However, in an AC current, we need to find out the phase difference and the direction, etc., because this is alternating. The direction alternates every half time period. So to get the value of power, what we do is we use the RMS values of both the EMF and the current, and then multiply that with the power factor. So ERMS is peak value by R2. IRMS is I0 divided by R2. That's peak value divided by root 2. And then cos phi is the power factor, and which is dependent on phi, which is the phase difference. So this formula can be used in all three circuits, or all kind of circuits, whether it's inductive circuit, capacitive circuit, resistance, LC, LR, RC, or even LCR series circuits. So all circuits can be used. We can use this. All circuits which contain alternating current. So again, we put the value of RMS values of the EMF and the current in terms of the peak value. So E0 is peak, I0 is peak. So then we divide it by root 2 as is the formula, and then we multiply it with cos phi in order to get the final formula that is 1 by 2 E0 I0 cos phi. Peak values and 1 by root 2 into 1 by root 2 is 1 by 2. That's simple multiplication. And cos phi refers to the power factor. So now let's look at an AC generator. So an AC generator is a device which generates alternating current. So what it does, it uses the principle of electromagnetic induction. So this principle is used in creating current, and in an AC generator, specifically alternating current. And so the elements used in an AC generator include a magnet to create the flux for producing the current, and then we need an armature, that is the coil, and then we need graphite brushes to take the current out, so to take the current away from the generator and towards the power supplies. So what we do is we find the EMF induced through the coil, and the EMF induced is given by this formula. So E is EMF that is induced, and then we have N, B, A, omega, sine omega t. N here refers to the number of coils. We have B and A. A refers to the area of cross section. So that's the area through which the coil passes, the flux passes through. That is A. And B is the magnetic field generated by the AC alternating current generator. So the AC generator produces a certain magnetic field to make current, so that magnetic field is represented as B. And so this is to find the EMF. So how do we find the current that's generated here? Well, that's pretty simple too. So we use the formula I is equal to E by R. So that's pretty straightforward. So I is the current produced, E is the total EMF that's already produced, and R is the resistance. So what we do is we use the value of E, that is NBA omega sine omega t divided by R. Now, sine omega t would refer to the nature of the alternating current because it has to change its direction every half period. And then we have omega, which represents angular frequency. That can be represented as 2 pi f, where f is the linear frequency. So that is all in all about the current and the EMF produced in an AC generator. Now, to find out both the EMF and the current using another formula, what we do is we find out E is equal to minus N2E1 divided by N1. So to explain these whole formulas, we need to look back here. So the formula here is E is equal to NBA omega sine omega t. So over here, E is proportional to N. And so in another device, that's the transformer, we'll be studying how to minimize or maximize voltage. So we need to step up or step down voltage. So E is proportional to N, so that means E1 by E2, a ratio, would be the same as N1 by N2, another ratio. And so over here, by cross multiplication and further simplification, we get E2 is equal to minus N2 E1 divided by N1. And similarly, we get I2 is equal to minus N1 E1 divided by N2. Now, since current and that has a looping factor or something, so that it effectively makes N1 come on top and N2 come on the bottom in the current formula, while N2 comes on the top and N1 comes on the bottom in the E2 formula. So that concludes AC generators. Let's move on to the final part of this tutorial, and this deals with transformers. So over there, we found out that if N2 is greater than N1 and N1 is greater than N2. Let's go back and see. So this is actually used for transformers and not for AC generators. So what we found out that when N2, the number of coils in the second part, is greater than the number of coils in the first part, it's step up. And when it's vice versa, it's step down. So this refers to transformers. But what is a transformer? So a transformer is a very important device, and this device is used to obtain a high AC voltage from a low voltage AC source or vice versa. Now, AC is produced in really low voltages, such as like DC, but however, to transmit AC, you need to have minimum power loss. So for that, they convert it into a very high voltage AC current. So then there is minimal power loss. However, we can't use this voltage in our homes. Our homes have only like 230 volts. It can only support that. While in power lines, it's 11,000 volts. Scary, isn't it? It's a very big value. So the important intermediary here that is used to convert the values of the voltages is known as a transformer. So what it does is it uses the property of mutual induction, and it either increases or decreases the voltage as required. And a transformer is basically a rectangular coil of soft iron core with coils wrapped around it. So let's say this is N1 and this is N2. And if N2 is greater than N1, so the number of coils wound on the output is more than that on the input, then what it does is it becomes a step-up transformer. So step-up means it is used to obtain a high AC voltage from a low voltage AC source. Now, suppose if it was the opposite. So if we had a lot of winding on the first coil, but in the second coil, we don't have that much. That is known as step down, and what it does is it decreases the voltage. Now, this setup in an ideal situation is 100% efficient. However, in real life, there is no ideal transformer, and so there is always some loss of power. That can be measured by using the efficiency. So the efficiency, which is expressed in the terms of eta, this symbol, is represented as output power divided by input power. So the power of the output supply of current divided by the power of the input supply of current. That gives you the efficiency and the power loss. And although we can't achieve 100%, we can easily achieve 99% efficiency using some very simple tricks to minimize power loss. And so that ends this tutorial on AC current. So what we see is that we've finished up with alternating current. We looked at the AC current in general, the contributions to it, the two quantities, impedance and reactance, the various circuits from LCR, LR, LC, RC, and LCR series circuits. Then we looked at power in any AC circuit, and then we looked at AC generators and transformers. So this is the basic backbone of this chapter. And so, did you know that Brain Blitz Audios is a quality educational channel dedicated to providing free content to all? Free educational content is viewed from this channel. Now, to be a part of our journey, please subscribe to our channel. We'll be back with more interesting videos and tutorials on this physics, chemistry, as well as other interesting content such as learner words, poems, stories, etc. So until then, take care, stay safe, see you in the next episode. Ta-ta for now.